Good afternoon, everyone. My name is Alessandro Carmona. As you have heard, we have met almost more than 10 years ago. I'm very happy to be here today because I have worked with a few of you. I have known many of you from not only the collaborations, but also from reading your very interesting papers. So it's a very honor to be here for me today to share what we are doing in this project. I would like to say first that a first disclaimer that what I'm about to share with you is not experimental results that we have obtained in the lab. Although I do feel I have a strong background in the experimental field. What you will see today is mainly an analysis that we have conducted in the REFOR Industry project, which is a project which is focused on helping the industry, the energy-intensive industry, to decarbonize its processes. You will see afterwards. These are the main goals that I'm trying to achieve during my talk. I will try to show you I'm aware that you know very well this topic, but I will show you the contribution of the industry to all these emissions that we need to remove from, we need to start avoiding, and we need to remove from our planet in order for us to survive. And also, I want to show you some of the decarbonization solutions that we are exploring in this project, REFOR Industry project. And finally, the main topic of the talk. In order to decarbonize deeply the industry, specifically the industry of Europe, we need to think about other possibilities, not only applying renewable energy solutions, bio-based solutions or thermochemical solutions, but also trying to think what to do with the carbon that has to be removed or captured and converted into something of use. And I will focus here especially on a few synthetic fuels. I have included only two slides of what we do in CIRCE. I come from a technology center located in Zaragoza, Spain, but we also have presence in Brussels, as you might expect, in order to attract funding for our activities. And we also work in different countries, especially doing projects for the knowledge transfer to companies, to other entities. CIRCE can be described as a very young research center, but we have I would say it proudly, a good history on technology transfer. That is our main essence. We identify technologies that are able to help the industry, mainly in Spain, as you might expect, but also we work with other companies in Europe. What we do is mainly focus on three different activities. So as you know, we do some research. By doing some research, we produce knowledge that we can transfer afterwards to companies, especially. And of course, we do some education part in which we provide knowledge in different seminars or conferences like this one. Just two slides about the project that is the main basis of this talk. REFOR Industry project is focused on trying to identify different renewable technologies to decarbonize the energy-intensive industry. It is a European-funded project, and as you might expect, since we are in this symposium for biotechnology engineering, many of the solutions that will be useful for the industry are renewable solutions that are available right now, or that might be available in 2030 for the industry to decarbonize its processes. When I say decarbonize, I refer to those processes that the industry uses and requires electricity and heat that usually comes from fossil fuels. So the project is mainly focused on these different aspects, and we have conducted an analysis in order to see how the different technologies, renewable technologies that you can see on the slide, are available for the industry. We have as well published a few results on this. As you might expect, we are considering different industrial sectors. Afterwards, I will show a few slides of this of the most emitting CO2 emitting sectors, but we have mainly focused on the steel and cement sectors. Afterwards, I will show as well a few examples of how these technologies are applied for the steel sector, especially how CO2 can be used, captured in these sectors to be converted into useful synthetic fuels that are currently being produced at a few exemplary companies. This analysis is available already. You can download it and see the roadmaps that we have been analyzing in the project and how the project has helped us to suggest identified roadmaps or a group of solutions that the industry will require in order to decarbonize the different industrial processes. I will also start by giving a simple classification of different pathways for CO2 use. I'm aware that you are familiar with many of these technologies. Once the CO2 is captured, can be used in multiple processes. The CO2, without any additional conversion, can be used, for example, in the food and beverage industry. We are aware of these applications, but carbon can be also converted to give an additional value. And I will focus especially on a few of the synthetic fuels that can be used and are already being produced at the industry. Of course, we have very interesting applications focused on the production of other type of chemicals, other type of bioplastics, for example, or also building materials. But these applications are out of the scope of this talk. I'm aware as well that since we are in this conference, that you are familiar with this. I won't give details of this, but you know the different definitions of biofuels that exist. This is the most simple one, the most well-known biofuel that can be recognized. That is the production of, for example, ethanol, biodiesel from food crops. It's something that that Europe is trying to avoid in the following years. It is hard to do, but something that can be achievable. As you might expect, these type of fuels, biofuels, have a dilemma whether you produce food to feed the people, or you produce food crops to feed our cars. So this is the main dilemma that the first generation of biofuels has. Therefore, we need to focus on other alternatives for biofuels. There have been several talks today regarding the production of biofuels from biomass or from other industrial waste that can be converted into biofuels. However, as you might expect, CO2 can be as well a good source, a good feedstock for biofuels production, and also for fuels that can be produced with thermochemical processes. For those who are not familiar with this second generation of biofuels, but I'm aware that many of you are familiar with this. Biofuels can also be produced from multiple wastes coming from crops, industry, livestock, and food. We have seen talks today coming from hydrogen, coming from food waste, biogas coming from sludge. So this could be the second generation of biofuels that can be identified in this scheme. Regarding the different technologies available for this biofuels production, we have biochemical conversion. We have seen as well a few talks for the production of hydrogen, biogas, and other type of fuels. But we have also other thermochemical conversion processes that are already available for the industry to use waste for the production of fuels. Eric Travely told us a few hours ago regarding the gasification of biomass, if I remember correctly. So that is a quite interesting option to produce hydrogen from biomass waste, agricultural waste, not to use biomass that can be used for other type of applications, but the option is there. Regarding another definition of more advanced biofuels, we have multiple microorganisms that can be engineered, modified in order to obtain biofuels or bioproducts. I will focus mainly on the biofuels that can be used by utilizing microorganisms and CO2 as a feedstock, which is as I said before, an alternative for the industry to decarbonize its processes. So here we have an opportunity because genetics tools are not still well available, but they can be developed in the following years. And there's also seems to be an engineering challenge in order for the scale up of the technology, as Eric Travely mentioned before. But I will show you afterwards a few examples of how this has been already achieved and how we can all together put our efforts in order to bring this technology for industrial application. I'm aware that you know this situation quite well. We all produce huge amounts of CO2 in our daily activities, not only in our cities or by driving our cars, but also the industry is quite important emitter of CO2. What you see in the slide is the different emissions by different regions in Europe. I have to say that what we have analyzed in the project is mainly focused on Europe, but I'm aware that multiple regions in the world have the same problem, although they might tackle the situation in different ways. But the information that I will show you is mainly focused on Europe. As you can see that the European Union has a very well established strategy in order to decrease these emissions by 2030 first and by 2040 and 2050. So the European Union, for those who are not familiar with this, has set very ambitious goals in order to decarbonize completely its activities by 2050. This is quite a challenging task because the technology is not available there in order to accomplish this, but we will try to do it all together with solutions presented here today. As I said before, the different sectors in our daily life contribute to these emissions. What you see are here in the slide are the emissions from 1990 to 2019. As you can see in Europe, they have been decreasing slowly, but they have been decreasing, but there is still plenty of things to do. And especially this project is focused on how to tackle the emissions from the industry. By the industry, I mean especially energy-intensive industry. These are steel producers, cement producers, aluminum producers, and also the chemical sector. What you see in the slide is the emissions of different industrial sectors in Europe. As you might expect, the cement and the iron steel sectors are the ones producing the highest amount of CO2. Also, the chemical sector and the extraction of oil and gas. But the project is mainly focused on those industries that are able to produce steel, cement, and chemicals. We have excluded from this analysis the food and beverage industry and also the pulp and paper industry because they have already applied multiple solutions in order to decarbonize its process. From the different emissions that you have in each industrial sector, we have that an important part of these emissions comes from the combustion of fuel, fossil fuel. So if you provide solutions to substitute the fossil fuel they currently use, you are tackling a very huge problem of the industry, as you see in the slide. Some of these solutions, I have shown them already in previous slides. We are considering different type of renewables and how this can be implemented at the industry. But as you can see, there are as well other solutions that in the long term, in 2030, 2040, 2050, can be applied in order to deeply decarbonize the sector, because the industry can substitute certain fossil fuels by, for example, biomass, which is highly debatable in Europe, but it seems to be applied soon by many sectors. But other technologies are required, because biomass, for example, or other biofuels have a limitation of availability. So you need to provide solutions different from the ones already available. And some of these solutions are based on the production of additional biofuels from CO2. So first of all, you need to retain those CO2 emissions and make use of those CO2 solutions into the production of biofuels that can be used at that specific industry or by other type of sector. Now we come to our good friend, hydrogen. We had as well a few talks before regarding hydrogen. I have been working with hydrogen, or I will say I have been in contact with hydrogen experiments since my studies at the university, and it has been promised in 2005 that hydrogen is the future, the fuel of the future. So far, into 2022, we have not seen, sorry Eric, we have not seen any industrial application of, hopefully we will see it, but we haven't seen any industrial application for biohydrogen production. I hope I can see it someday, but it seems to be getting harder to bring it to that specific level. I wanted to include this definition of the different types of hydrogen that we can find, because in order to really decarbonize something, we need to provide synthetic fuels that are a product from CO2, captured CO2, and hydrogen, green hydrogen, that is mainly produced by electrolysis processes or other type of processes that do not use fossil fuels in the production of that hydrogen. So, which is as well quite complicated in Europe, because as we have seen previously, most of the hydrogen in Europe is produced from fossil fuels, but there seems to be, as you can see in the slide, there seems to be quite good plans in the coming future and also in the mid-long term, in Europe at least, to produce hydrogen from all the different renewables available. I must confess that the analysis of the availability of renewable power for the production of green hydrogen, it's highly dependable on the region that you consider in Europe, because although all the countries have a certain amount of renewables, for example, Spain has quite a huge amount of photovoltaics and also wind, less wind than photovoltaics. So there seems to be that Spain, at least, is one of the front runners in the production of green hydrogen coming from 100% renewable energies. That's why there might be an advantage there to produce this hydrogen that is required for the production of synthetic fuels. One of the issues is that green hydrogen nowadays is quite expensive, at least for the industry. They are not willing to pay that much, or that price of around 10 euros per kilogram of hydrogen. They are willing to pay less. They are expecting to have a price quite cheaper than that, around 1 euros per kilogram of hydrogen. So this will be mainly dependable on the development of renewable power that is available in the continent. However, one of the main possibilities for hydrogen to be cheaper in the coming future is the the development of other technologies that require hydrogen as feedstock. So here we see an opportunity, at least in the analysis that we have conducted in the project, in order to see the reduction of green hydrogen price in the coming future as a feedstock for synthetic fuels. I have already told you the different industrial sectors that we are considering the project doing our analysis, but we are mainly focusing on those sectors that do not have a very specific solution for the decarbonization of the industry. And we are focusing mainly on those sectors that produce a huge amount of emissions and emissions that contain a high amount of CO2. What you can see in the slide are three sectors: cement, steel, and chemicals. They currently produce a good amount, huge amount of emissions, which high content of CO2. So this can be an opportunity for the industry to focus the efforts of the development of technology on these three specific sectors, at least in Europe. They have a high CO2 concentration in their emissions in comparison to other sectors. And here you can, the good thing is that many technologies for the capturing of CO2 are already available. So our colleagues who are working mainly on gas fermentation or gas analysis might have additional information on this, but CO2 capturing technologies are at a commercial state, and they are already available for the industry to be applied. And we should also focus on those different technologies that are able to produce higher concentrations of CO2, like oxy-combustion, pre-combustion, and post-combustion. This will mainly depend on the sector that you analyze, but we have to focus on those technologies to capture that CO2, use it for additional processes. As you might expect, and as I said previously, thermochemical processes are already available at a commercial state. They are already applied at the industry for the production of hydrogen, CO2 from fossil fuels. They are already available there. They can be applied for the production of additional synthetic fuels without the need of microorganisms. But since we are in a biotechnology conference, let's talk about biotechnology-related processes. I won't talk about very advanced or very novel processes. These are well-known processes by all of you. So we have the gas fermentation. Also, colleagues working on gas fermentation are quite well familiar with this. And also hydrogenotrophic methanogenesis is also quite well available. They can be also used for the decarbonization of the industry. So as long as we have CO2, a good CO2 source, and also green hydrogen coming from different technologies, renewable technologies specifically, we can make these two synthetic fuel production processes more available for the industry. Here we have an advantage from the biotechnological point of view. We have multiple microorganisms. I'm aware that many of you are working on different fields utilizing different microorganisms that can be used in order to produce synthetic fuels. They have advantages and disadvantages, but if we complement the way these microorganisms work, we might have a good we might have multiple microorganisms in order to produce different synthetic fuels. But I will focus mainly on those microorganisms able to produce synthetic fuels from CO2. One of the aspects also mentioned today, and also I have seen a few of the posters, is the use of microbial electrochemistry for the production of CO2, of synthetic fuels. although I have worked here in the past with our colleagues from INRA and Arbonne with these type of systems, nowadays I'm not 100% sure whether this can be fully applied at an industrial scale, because although these type of systems are quite interesting from the biological point of view, from the electrochemical point of view, the research required in order to bring these type of technologies to the industry and to the specific time when we need this, which is in the following 5 to 10 years, might not be enough. But you have the technology. Microbial electrofuels are produced, molecules are produced using this technology by using a bioelectrochemical system. You have seen already a few slides and also a few posters. A bioelectrochemical system is evolved from fuel cell systems in which you use microorganisms instead of hydrogen as a fuel. I will apologize with my colleagues because I have included this slide of unpublished results. I hope we can publish them soon. But as in order for you to have an idea of what microbial electrochemical system is, you can find it in the slide. And finally, a few of the main gaps in this technology are how these microorganisms interact with the electrode. That's why I said that there might be we might need several years in order to completely understand and bring this technology for the industrial applications. However, the concept is there. We can try to combine CO2 with renewable power in order to produce synthetic fuels with this technology. And afterwards, we have produced a very simple molecule. We can try to elongate that molecule to produce additional, further, more interesting molecules, specifically for the fuel sector. But we will see. There are different groups here, like the group from Argentina, which are applying all the knowledge in order to bring this technology to industrial scale. The example that I wanted to share with you regarding the industrial application of synthetic fuel production is the one you can see in the slide. This example has been applied in Europe and also in China, if I'm not wrong, by a company. They have applied the capture of CO2 from the production of steel. That capture of CO2 stream, it's clean, and afterwards is fed to a bioreactor in which they have a culture of Clostridia. Probably you are aware of this example. You can find it in Belgium. They have in the bioreactor a very defined culture, a very specialized culture of Clostridia that produces CO2, that produces ethanol from CO2. So they have a very nice example, industrial example there, because they are currently avoiding CO2 emissions and converting those emissions into ethanol that can be used afterwards by the transport sector. And this example is quite interesting because they have closed the loop. So part of the biomass that is actually being produced in the system, they are actually considering that biomass to produce biochar. Biochar, it is quite known product that can be produced or can try to imitate the physical characteristics of coal. So this industry requires huge amounts of coal. So by using that biomass, which is under development, I will have to say, they can produce their own fuel for the process, closing the loop of the industry. So we have here a very nice example of how this can be achieved. And if you need additional information of this, you can have a look at the MUSIC project, which is as well a European funded project. You can see here on the slide the picture of the company, of the plant. They are, as I said, this is not a basic research. This is not a pilot scale project. They have already applied this. We have visited the place. It's quite interesting. and they are, you can find pictures of this example online. So they have already completed the plant, and they have already been starting producing that ethanol from CO2 emissions. So we are closer to bring those solutions that are required for the sector. This is one of the examples that they have allowed the people to publish regarding the operation of this type of reactors. As you can see in the example, 100 days of operations are quite a good example of how robust this type of system is. And you can see here as well the feeding of CO2 and also the production, the constant stable production of ethanol. So another example of the success of this type of biotechnological applications for the production of synthetic fuels required for the industry, for the decarbonization of the industry. The final example I will share with you, this is something that the people working mainly in Europe, close to Germany, probably are aware of this. This is a company which claims to produce additional biomethane from the mixture of CO2, which can be industrial CO2 from the combination with hydrogen, in the renewable hydrogen. So this type of solution can also be applied to the industry in order to decarbonize the sector. I would like to finish with a few takeaway messages. The CO2 utilization through different microorganisms is a very promising technology, and also an available technology for the decarbonization of the industry. I didn't talk about microalgae, but microalgae are as well a really nice group of microorganisms able especially for the capturing of CO2 into biomass, which can be used additionally into the production of biogas in anaerobic digestion. We have as well all type of lithoeutrophic microorganisms for the fixation of CO2. Although many of these microorganisms are not available already for the industrial applications, we have them, we know them, and since we have certain tools to modify these microorganisms, we have plenty of possibilities to capture CO2 and convert that CO2 into synthetic fuels. And finally, something that I didn't mention in the talk is that in order to successfully apply all these type of technologies, we require, of course, the technology to be available, to be developed at the industrial scale, but also the policy framework, which is, I admit, quite a boring topic to talk about, but the policy framework should be quite well established in order to successfully apply all of these technologies. I will finish with an open invitation for those that are involved in the development of solutions for the decarbonization in the industry. We have 3 events, closing final events of the project. One in Zagreb, which is mainly an interaction with solutions in the country, in Croatia. We have as well one final event in Brussels, in which we will mainly discuss the policy framework required for the industry to apply these solutions. And one very final event in Spain, where CIRCE is located, where we will discuss and share the successful cases of industries at the country in order to decarbonize. Thank you very much for your attention.